Thank you very much. Thank you very much for the invitation. I'm delighted to be here. And probably some of you have noticed that the title that I announced in the beginning was different from what I'm supposed to do now. And if you're not happy about it, you prefer the other talk, you can blame Stefano, because he convinced me maybe this is better for this audience. Okay, so as the title suggests, I'm talking about homogenization for Hamilton-Jacobi PD and Hamiltonian ODE. So let me start with some introduction, some of the questions that are interest, and try to relate these two questions. So if you have a Hamiltonian function, that would be a function that depends on position, momentum, or in general, position, momentum, time. This function appears in two contexts. The first context is in the statistical mechanics when we are interested in scaling limit of certain, we are in the growth, we have a stochastic growth, and we are interested in the macroscopic behavior of the interface. And the other context is when you have Hamiltonian ODEs. So let me explain these two contexts and try to relate them. So again, here X is in RD. You should think of it as a position. P is in RD. That's the momentum. And T is time. And in the first context, we are interested in Hamiltonian ODEs. Which means that you want to solve an ODE of the form X dot is HP. XP, let's forget about the dependence on time for simplicity. And by sub-indices, I mean partial differentiation. And you would like to solve this ODE for some initial condition. So let's say X and P at time 0 is some vector A, which is in R2D. And under some kind of standard conditions on H, you can guarantee there exists a unique solution. And let me write phi t A for this solution, Z of t, which is X of t, P of t, to have a notation that also displays the dependence on initial condition. So if I want to kind of have a nice picture to compare the various contexts in which you have a Hamiltonian function, the picture would look like this. You have the set of all possible Hamiltonian functions that are denoted by H. So this is the space of nice Hamiltonian functions. So you give me some Hamiltonian function, and out of that, I can build a flow for you, which I denoted by phi ht. So you have a flow here. So you should think of this as the space of flows. Which is exactly this guy. And in fact, for many questions in dynamical system, you may even specify t equals 1 that would yield a map on R2D that I denoted by phi super H. And it turns out that this space that, let's have a name for it, for example, let me call it K. This space is the space of symplectic maps. So let me make a remark here that for each t, phi th is a symplectic map. This means that if you write A for the derivative of this transformation with respect to space and momentum variables, then this matrix enjoys the following identity. J A A transpose equals J, where J equals the matrix 0, identity, identity, 0. And here you should think of this as space, and here momentum. So this is D by the identity matrix. In fact, there is a short compact form of this ODE. You can rewrite this ODE as Z dot equals the matrix J times the gradient of the function H. This is a full gradient including the position and momentum. And you know, this is kind of the kind of ODE you have, and it turns out that the derivative enjoys this property. So you start with Hamiltonian function, you can have a flow, and you can have a map that is symplectic. So this is one context that we are interested in a Hamiltonian function, but there is another context. So let me kind of explain it here. Given H, we may consider the PDE ut plus hx ux equals 0, and for this, you need some initial condition, where again, the sub-indices, they denote the partial differentiation. So here you have the time derivative and spatial derivative. And here u is a function is from Rd cross 0 infinity into R. When you solve this PD under some conditions on H, you can guarantee there exists a nice solution. Once you have a solution, perhaps to have a notation that displays the dependence on initial condition, perhaps I write it as STGX for the solution. And in other words, I have a family of operators that act on functions. In fact, if you put some nice conditions on H, you can guarantee that if initial condition is Lipschitz, then at later time you have a Lipschitz function. So you should think of ST as an operator that acts on space of Lipschitz function. So think of this as a space of Lipschitz function. And needless to say that in a nice situation, this enjoys some semigroup property, and there are other properties that would be of interest to point out. So out of this H, I'm going to give you a semigroup. And I write S for the space of some nice semigroups. And of course, needless to say that you may set T equals 1, and then you have just a map, maybe I denote it by F, that is that kind of defined on the space of Lipschitz function, and I denote it by SH1 for S, maybe SH for SH1. Okay? So out of H, there are two routes to take. You may consider the corresponding Hamiltonian ODE and have a flow, which is symplectic, or you can take, you can consider that PDE and build a family of semigroups. And now the question is whether they are related to each other. And the other question is that what are some interesting questions you can formulate for these two problems. So let me discuss two questions that are of interest in this business. Two questions of interest. Question number one. Let me start with this setting. In this setting, the following questions is of interest if you regard U as some height function that would be of interest in statistical mechanics. So consider, regard U as a height function. So if I want to draw a picture, this is x, and this is u at time t, So this is some kind of height function. And think of this height function as an interface, the graph of this height function as an interface separated in different phases. And we may regard this as a microscopic model of an evolving interface. This basically says that if you want to know with what rate the height function changing with time, then the rate depends on where you are and what's the inclination of that interface, the inclination of the interface, which is quite a natural model for a growth. And if this is the microscopic model, you want to rescale it to have the corresponding macroscopic parameters, and you want to pass to the limit to have a reduced description for the phenomenon you're interested in, and that reduced description could give you a macroscopic kind of characterization of the model that you are studying. So for that, you take n, which is very large and positive, and you rescale time and space in this manner. Which basically says that if x is a macroscopic parameter, you multiply it by a big number to take the corresponding microscopic parameter, and you speed up time. Then this u would be the microscopic height. If you divide it by n, that would give you the corresponding macroscopic height. And the question we are interested in is whether, under certain conditions, the limit of this function exists. Now, one can easily see that the function un now satisfies the following PDE. And needless to say that you want to solve this for an initial condition. And then if some averaging happens in an ideal situation, U bar also satisfies the Hamilton-Jacobi PDE, but now somehow the space variable is averaged out, and the outcome would be also Hamilton-Jacobi for which the Hamiltonian function is independent of position. So ideally, as n goes to infinity, you want to get a system that looks like this. And that is exactly the question of homogenization. So if you think about it, what's happening is that you give me some h, but then out of this h, you produce a family of Hamiltonian, which could be very oscillatory. So this kind of suggests defining a group of transformation that is acting on the space of all Hamiltonian functions. And in some sense, you want to say that this gamma and h converges to some h bar. But needless to say that this is not a pointwise convergence, it's rather very weak convergence. And basically, you have you have a group action here. So this is a group action. N here is positive, so it's in R plus. This is a group. This group is acting on the space of Hamiltonian. And to address the notion of convergence is much easier to address it here. So I'm saying that the hope is that when you look at gamma and h, this sequence converges to some h bar that now it belongs to a subspace of semigroups here, or alternatively I can kind of formulate it like this. So you have this sequence, this family of Hamiltonian. This converges presumably in some generalized sense to some h bar that belongs to some subspace of h, and this subspace is the space of Hamiltonians that they don't depend on position. And needless to say that this is pretty compatible with what we are doing here, namely taking the limit of this sequence. And if the limit exists, the limit somehow is invariant with respect to this group, which is very much the case if h bar is independent of position. So this is one context that we would like to study. So what would be some of the questions you can address in this context? So let me address a second question, which is of interest, and I can compare the two. So let's see. Let's see if I can get this right. Maybe I send it all the way up there. For my nice picture, I think that would be a good place to stay, almost in the heaven. Okay, so now the only thing is I can't see it. Impossible. Okay, so now I want to formulate question number 2, which very much you encounter in classical mechanics. So in question number 2, you give me that Hamiltonian ODE that depends on position and momentum, and that's very hard to solve. And the wish is that maybe I can make a change of coordinates and turn that Hamiltonian ODE to another Hamiltonian ODE that is much simpler to solve. So the question is there a change of coordinates, call it psi, which maps lowercase variables x and p to uppercase variable x and p so that the ODE z dot j gradient h z becomes, maybe I use uppercase also here, so uppercase z means uppercase x and uppercase p. For which this is much easier to solve. This is a very classical trick that we've seen with some success in some very limited number of examples. Now, it turns out that if you take such a change of coordinates to guarantee that the outcome is again Hamiltonian ODE, I mean, you can make a change of coordinates and turn ODE to another ODE, but the result may not be again Hamiltonian. In order to guarantee this psi better be symplectic. So if you take a symplectic change of coordinates, then you can guarantee the outcome is again as a Hamiltonian ODE, and the relationship between the old Hamiltonian H and new Hamiltonian H bar is very simple, and is simply given by the formula that H bar, H, for example, is H bar composed with psi. It's as simple as that. Or the other way around, maybe. So I define, yes, that's correct. So that's a relationship between the two. But then how can I guarantee that this new system is easier than the old system? For example, if this new system, H bar, is independent of uppercase X, then I have a very nice situation that I can easily solve. So the goal would be that H bar is indeed a function of P only. Now, another thing happens. You see, what is significant about Hamiltonian ODEs is that even though you're dealing with an ODE in dimension R2D, the vector field is determined fully in terms of a scalar value function, and that is H. There's a lot of structure going on because of the very form of the right-hand side. For example, right-hand side is divergence-free vector field, but there is a lot more in there. There's a lot of structure going on here. Now, it turns out that also, if you have a symplectic map, then at least locally, you can associate a scalar value function to this map that is known as generative function that gives a very nice description for the map. And so at least locally, psi has a generating function. Maybe I call it W. And now there's some, you have to choose W in a careful manner. You see, there are lowercase variables here and uppercase variables there. But if you kind of think about the symplectic property, there's some form, 2 form is preserved. That 2 form, there's a minus sign in it. And it suggests that perhaps to have a nice description for this generating function, you want to choose the dependence of generating function to variables in a twisted way, because of some minus sign that shows up in some differential form. And for example, I may choose a function W that depends on this guy and this guy, as opposed to depend on these guys or those guys. So if you do it in a twisted way, for example, W that depends on lowercase x and p, then then you can kind of recover the other two variables in the following way. Namely, for example, the uppercase, the lowercase p would be wx xp, and the uppercase x would be wp xp. And if you substitute this p in this formula, which can be written as h bar of p equals to h of, so here I have lowercase variables, but if I substitute this for the lowercase variable, I end up with the following formula. Which, when you fix p and vary x, can be regarded as Hamilton-Jacobi PDE. So you see that for this classical problem, you may end up solving a Hamilton-Jacobi PDE. And in fact, this Hamilton-Jacobi PDE doesn't depend on time because I assume the Hamiltonian is independent of time, but in reality, this Hamiltonian may depend on time, and you may even choose this guy to depend on time. If you take that into account, then you have a kind of Hamilton-Jacobi PDE that also has time dependence and would resemble this, except for an additional constant that shows up on the other side. So, so indeed, you have a situation when Hamilton-Jacobi shows up in here, and believe it or not, it turns out in some questions of interest, the reduced Hamiltonian H bar that shows up there coincides with Hamiltonian that shows up here. Do you have a question?
Yeah, which are same one.
Which one?
Upper H bar and the lower H bar.
It turns out in some cases they coincide, not always.
Not always.
So, remark, H bar of 1 equals to H bar of 2 in certain cases. Okay, so now you may, yes?
So, you give the definition of psi has a generating function.
Psi? Psi?
So psi has generating.
The generating function. So the generating function basically means find a W for which these are true. You can regard that as the definition. But the question is why such a function should exist. It turns out, so you see when you write it this way, one is Wx, you want to differentiate with respect to P and differentiate this with respect to X and match these second derivatives or something. It turns out when you write it down, that would be equivalent for the transformation to be symplectic. So the fact that such a W exists, at least locally, is equivalent to symplectic property. Okay, makes sense? So far, so good? Okay, now, now you see, there are various questions you can ask. For example, here, you can kind of wonder whether this problem can be solved as a PDE problem. I mean, if you write down a PDE, you have a good chance to solve it. But then once you solve the problem, it's not clear out of this solution, you can build this psi globally. But that's too much to ask. If such a global psi exists, that's equivalent for this ODE to be completely integrable, which is a very rare thing to happen in reality. However, the existence of PDE is not something rare. And you may wonder, what would happen if I start from the existence of a solution and try to say something intelligent about the corresponding ODE? That's one question we can ask. So a natural question is, suppose solve the PDE, let me call it star, solve star. Can we use W to say something about the ODE, about the original Hamiltonian ODE? So that's a natural question to formulate. But then now the question is, what do I mean by solution? And that, yes?
Just a question, in the first case, in the one, it's expected that you have only one H bar.
You have one.
You get one homogenized. And why would you have to say that you have equality, but you never say that?
Okay, you put conditions. One has to be careful here. That's absolutely correct. So under certain circumstances, you can formulate conditions, and then you will see that the constant unit here is unique for every p, but then I have to give you very precise formulation for my expectation of function w. So you can kind of I get to that later. For example, I have to put condition, in general, for general H, this is helpless. You need more structural conditions on H. When you put those conditions, then I can give you a more precise formulation of this equation, then you will see the constant H bar p is unique.
Okay.
For every p, such a constant exists and is unique. Otherwise, if you put another constant, then such a solution doesn't exist. You see, that has to do with the behavior of this function as a function of p. I have to put a condition on the behavior of this function, which somewhat resembles the fact that my original goal was to construct this transformation. For that transformation, I need some non-degeneracy. So what that means exactly. So when you kind of formulate these correctly, then you have a well-defined question for which the constant would be unique. Okay, so but you know, in all, you're basically talking about a transformation A that goes from the space of all Hamiltonian to a space of certain Hamiltonians. These are Hamiltonians that are independent of position, and that would kind of send H to H bar. This transformation is highly non-trivial, and it has some consequences for the PDE problem and the ODE problem. So I'm going to be kind of more precise, but that would be the goal. But you know, but if I formulate it this way, one may wonder whether I can start with a solution to this PDE and say something intelligent about the corresponding ODE. But for that, I have to be more precise about what notion of PDE I'm talking about. As we've seen in this workshop in several occasions, the Hamilton-Jacobi equation does not possess classical solutions in general. So it matters what type of solutions you select. So for that, let me address another question. The other question is, now, when we go back to the first setting, when this is a height function and you have a growth, a natural way to come up with a correct notion of solution is that to add a viscosity. When you add a viscosity to this equation, send viscosity to 0, then you get the notion of viscosity solution. So one possibility is that, viscosity solution. Okay, so let's take this for granted. From now on, I'm going to consider viscosity solution to Hamilton-Jacobi PDE and address that question, namely you rescale your Hamiltonian or rescale the solution to the Hamiltonian or semigroup, whatever you have in mind, and then you wonder whether the limit exists. In general, of course, you don't expect the limit exists at all. There's no reason for the limit to exist. But it turns out that, for example, so case 1, if H is coercive, in some sense, coercive means that as you send the momentum to infinity, then H goes to infinity uniformly in position. For example, then homogenization occurs, or homogenization is true. So this is a classical result of Lyon's, Papanicolaou, Fraydoun, and this is a paper in '88. So if you assume the periodicity, this operator makes sense, you can define it, and it would allow you to pass the limit. Now, so you have that, Now you may wonder whether using viscosity solution in that setting, whether I can say something intelligent about the ODE. So how about, so now scenario number 2. How about the Hamiltonian ODE? So can I solve that PDE a la viscosity and wonder the solution can be used to say something about the ODE? And in fact, this is a classical theory that has been established only when Hamiltonian function is convex in momentum, not for general Hamiltonian. That has not been well understood yet. So when HP is convex in P, then according to matter theory, so matter theory is formulated in terms of Lagrangian formulation for Hamiltonian ODEs, and if H is convex in momentum, you can also formulate the Lagrangian description of your ODE. And using variational techniques, matter theory would basically build an invariant measure for Hamiltonian ODE for which the support is given by the graph of that function, the function that comes from the solution. However, the PD side of the story was developed by Albert Fathy. So Albert Fathy, VKM theory. And many other people work in this area, but you can kind of find the details in a book that Fathy wrote on VKM theory, which basically says that solve the PDE for each P for, so now is the time that I give you precise condition to guarantee the existence of unique H bar P, and also for here, the function xp, basically you want to choose, since Hamiltonian is now periodic in position variable, you want to choose wxp that can be expressed as x dot p, so you have this quadratic function, plus some w hat xp, that now this guy is periodic in x. As this is common in this business, you don't expect this guy to be periodic, but modulo a linear function with slope p, then you can find the perturbation, periodic perturbation, that then you can solve that PDE for a unique constant on the right-hand side. There exists a solution. So you see, the fact that you have a linear growth here with this slope guarantees that there is a unique constant for which that guy has a solution. Otherwise, it doesn't have any solution. And then one can construct an invariant measure for the ODE that with support, its support is exactly the graph of the derivative. So for each P, look at this set, for example. For each uppercase P, take the solution. So now you have a family of invariant measures that you build for the corresponding ODE. And there's a lot can be said about this. You see, again, this is not well defined everywhere. So you have to restrict it to those X for which this derivative exists classically and the support lies there. So there are kind of various things you can say here. But what about non-convex P? Non-convex Hamiltonian. So in this setting, it's quite natural because this PD still solution exists, and you may wonder whether that would yield something about the Hamiltonian ODE. And to make the story short, it turns out for non-convex P, non-convex Hamiltonian, the notion of viscosity solution is not the correct notion. what you get there may not be relevant to what we are interested in. Or put it differently, basically the viscosity solution says that you look at that ODE and you add some Brownian correction to that, small Brownian correction. You send the parameter to 0, the viscosity to 0, and it turns out that the solution you get W is not smooth enough so that when you pass to the limit, Brownian motion goes away, then it yields an invariant measure for the corresponding Hamiltonian, if H is not convex. When H is not convex, you don't have enough regularity of the solution W that would guarantee the limit would yield something interesting for the corresponding Hamiltonian ODE. Okay? So, but however, can we have homogenization for the ODE directly? You see, if you have such an homogenization directly, if maybe there's another formulation of homogenization you can kind of used for the Hamiltonian ODE, namely that box, the box on the right, and then that would be a good starting point. So maybe I can come up with another notion of homogenization, and I use that to produce some H bar for you, and then that H bar maybe can be used to say something about the corresponding ODE. So that would be the attempt. So the attempt would be to come up with a different notion of homogenization, which is different from the homogenization that I stated for the corresponding Hamilton-Jacobi PDE, or maybe I change the notion of solution to this Hamilton-Jacobi PDE. Maybe I come up with a different notion of solution that is compatible with the corresponding Hamiltonian ODE, even when H is not convex in momentum. So there are two ways to go about this. Either change the formulation of homogenization, or come up with a different notion of solution that is more compatible with the ODE. Okay? So moving in that direction, let me state a theorem of Viterbo, which kind of would be the first step towards matter theory in non-convex set. Okay, so let's go back to that picture. So maybe, I feel kind of lost here. You see, the picture is so high, I can't even see it. Maybe, hold on. Maybe I move this down now, down to earth from heaven. Okay, and at the same time, oh, I can do both at the same time. Okay, now it's earlier. Move those guys up. No. Okay. Likewise. Much better. So bad with this. I should have practiced before. Let's see. Finally, I'm getting the hang of it. Okay, so let's go back here. You see, you have here gamma n. This is a group that is acting on a space of Hamiltonian. Point-wise, this guy has no chance to converge. However, in a kind of artificial way, I can define a topology here that would say that homogenization means that this converges to H bar. What is the topology? Well, you go back here, you say a sequence H converges in this topology if the corresponding semigroup converges. In an artificial way, you can do that. Okay? So I can kind of say that in some integrated way, this thing converges, because after all, solving this PD, in some sense, you're integrating out your Hamiltonian. That's why the oscillation is averaged out, is damped. That's why you have a chance to have a convergence here. Now, you may wonder whether similar things is true here. Can I have a kind of nice topology here that says that somehow if these guys converge, that means the corresponding Hamiltonian converge? That would be more appropriate for questions you are interested in dynamical system. You're interested in Hamiltonian ODEs. Indeed, there are two topologies exactly on this space that people in symplectic geometry discovered and used that to say very interesting things about the corresponding Hamiltonian ODE. So there are two metrics here. one is called Hofer metric, and the other one is called Viterbo metric. And I'm going to tell you what those metrics are, kind of give you some rough definition. But the bottom line is that, yes?
In the compact setting or?
In the periodic case, but there's a little bit of extension in non-periodic case. Yes, I'm kind of assuming. I have to make some assumptions on Hamiltonian. In fact, Hofer metric, there's no periodicity, but Hofer has to assume that Hamiltonian is of compact support. In Viterbo metric, you can allow periodicity in space variable. At the first attempt, he has his metric defined for Hamiltonian that is of compact support in momentum variable. But you can also extend it to a situation when it's periodic in position and is coercive in momentum variable by approximation. So it's possible to define a metric for Hamiltonians we are interested in. Okay? Now, let me state the theorem, and this is Viterbo. I think it's maybe 2009, I don't remember the exact year, which basically says that with respect to Viterbo metric, so let me write it D Viterbo, this gamma and H does converge to some H bar for H bar, which is maybe a hat of H. So there is a way of associating a Hamiltonian function that is independent of position to every Hamiltonian function. And this A bar H coincides with the previous A, which you got it by doing homogenization using viscosity solution. This coincides with AH only if, maybe only if too strong. If, for now, let me say if H is convex in P. And there are very strong evidences that for non-convex Hamiltonian, they are not the same. They are different. Okay. But let me say a little bit about Hofer and Viterbo metric. Start with Hofer, which is much easier to define. And it turns out that Hofer metric is stronger than Viterbo metric. And you know, when I had this discussion with Viterbo, Claude believes that homogenization is not true with Hofer metric, which is a stronger metric. But it's easier to define Hofer metric. So how you define it? So remember this map, this is a time one map of a Hamiltonian ODE associated with Hamiltonian H. Now, you can give me a symplectic map that comes from different Hamiltonian. You see, here, if I take the whole flow, then that would uniquely specify the Hamiltonian function. But if I only give you the time one map of the flow, that would not specify uniquely the Hamiltonian function. So there's a lot of freedom. There are many, many Hamiltonians that they would yield the same time one map. So what Hofer does is that look at the set of all possible Hamiltonians that would yield the same time one map and take the norm of that Hamiltonian, L infinity in space and momentum, L1 in time, then minimize that norm. So basically, so in fact, first I can define a size of some symplectic, so you give me a symplectic map phi, I can define its size, and I use the size and use the fact that there's a group structure here to extend the size. It's not the norm because the space is not flat. It's not a norm, but it's a size, some kind of size of a flow of a map, and then you use that size to produce a metric. And this is the size, and you may regard it as the energy because Hamiltonian has the interpretation of energy. So that would be the minimum energy for producing such a symplectic map. In other words, this is the infimum of a norm of H, suitable norm of H, provided that phi H equals phi. And this norm is L infinity in Z, which is X and P, and L1 in time. Here, I have to allow H to depend on time, otherwise this metric is not well defined. is highly non-trivial fact, and that is closely related to symplectic rigidity, to show that if this phi is not identity, this minimum is positive. I mean, it's quite plausible that you kind of produce a Hamiltonian of very small energy, of very small norm, that it oscillates so widely that at time one can produce non-trivial symplectic map. That is not possible, highly non-trivial fact. In fact, if you change this L infinity part with any other LP, then this guy would be 0. Only L infinity yields something non-trivial. And so that's Hofer metric. What is Viterbo metric? Viterbo metric requires a lot of preparation to define. So what's happening is that you have this phi. Remember that certain phis would have classically generating function. It turns out general phi may not have a classical generating function, but if you allow additional dependence, you can create some extra variables, then you can define some kind of generating functions. So you take all possible generating functions associated with phi. Now, somehow you want to take the L infinity norm of that generating function as a candidate for the size. But that doesn't work because when you allow generalized generating function, you basically have a quadratic function plus a kind of bounded perturbation. So for the perturbation, you can talk about L infinity norm, but not for quadratic guy. The quadratic guy is associated with some kind of some symmetric matrix. If that symmetric matrix is positive, then you can talk about its minimum. If it's negative, then you can talk about its maximum. But that quadratic function in general is neither positive nor negative. So you have to look at a natural saddle point, critical point of that function. So you have this quadratic function for which you have a saddle point and is perturbed by an infinity function. Then there is a theory in algebraic topology known as Lusternik-Schneiderman theory that would give you a systematic way of locating critical points of such perturbations. When you apply that theory, then you have a candidate which is as good as L infinity norm when that quadratic perturbation is not there. That systematic way would allow you to define the size of this guy, and that is Viterbo's metric. And it is with respect to that metric that this can be achieved. Okay? So now, yes?
So I have a question regarding like this lack of, so the map from h to phi h, like is some sort of exponential map?
In Riemannian setting, yes, but I wouldn't call it exponential. Yes, you have an ODE, you look at time one map, yes.
It's like, generally, so I guess it is locally onto, so you get in space of diffeomorphisms or something like diffeomorphism?
Locally onto. I mean, of course, the map phi is diffeomorphism.
That means it's inside the groups that you reach. So,
inside the group you reach. You mean this guy?
Yeah.
I'm not sure what, okay, so if you give me a symplectic map, one question is whether that comes from some Hamiltonian ODE. That's a very subtle question that is still open in high dimension. I think maybe that's what you're, yes, that's an open problem. I'm not going that direction. So when I talk about K, I'm referring to those symplectic maps that for sure comes from Hamiltonian ODE, not arbitrary symplectic maps. Then I don't have to worry about it. So for sure they come from Hamiltonian function.
But regarding the fact that you have like different H's.
That's right. So, right.
So the generally, yes, they will be pretty far from each other. So.
That's right. It is true. So you see, here you have K. You want to put a metric here, or you want to put a metric there. But it turns out in this setting, it's more convenient. It's very important to put a metric on the quotient of this space. You kind of, you know, if you have two Hamiltonian that they yield the same phi, I regard that as a kind of, you know, it's the same thing. You know, that would belong to the same equivalence class. And I'm putting metric on the equivalent classes, and that makes this highly non-trivial and, you know, non-flat. Then, you know, finding a non-trivial metric that would respect the group structure. There's a group structure here. So this is invariant with respect to the group structure here. The group structure here is composing with a symplectic map.
And the Viterbo one doesn't do this infinite limit and this back like the group structure?
it turns out he still respects that group structure. You know, this generating function business is compatible with composition with symplectic map. There are all these tricks. Any symplectic map also has you know, there is a Lagrangian floating around. He uses Lagrangian and all that. Generating function is related to existence of certain Lagrangian. Yes, and his metric is also respects the group structure. So invariant with respect to the group structure, absolutely. Okay, so now let's go back here. Now, so this is the story for periodic setting. Now I want to go beyond periodic setting. Then I think I would fit in this conference because now there is some randomness. So how you go beyond the periodic setting? Okay, so how much time I have? I have another 15 minutes? 7 minutes. Oh, 7 minutes. Okay, so beyond periodic. Okay, so first, what periodic means? Periodic means you give me H, and I translate it. So let's define a translation. Tau A x P. This is H x plus A P. So basically, periodic means if you look at these translations, if you look at all possible translations of the Hamiltonian, that's a torus. In fact, if you equip the space of Hamiltonian with uniform topology, then basically, topologically speaking, you basically have a torus, because after one period, you're back to where you started. That's torus. Now, to go beyond periodic setting, one possibility is that you look at tau AH, you look at this set, and you assume that this set is pre-compact, and take the closure of it, and then you know, you can kind of use the fact that there is some group floating around. This is the group of RD acting on the space of Hamiltonian. You can build a group on here, and then take the Haar measure, and instead of saying that I have homogenization for each H, I would say that I have homogenization for almost all choices of H with respect to the Haar measure. So the support of that measure would be exactly the various transits of H or the limit points. If that happens, we say Hamiltonian H is almost periodic. And some topology is left. So this closure would have the topology of some you know, compact topological group. That's almost periodic scenario. But probabilists have an alternative way of doing things when the topology is completely lost. So what we can do is that instead, you go back to the set of all Hamiltonian functions, you try to put a probability measure directly on that, which is the analog of Haar measure in the previous setting. You insist that this probability measure to be invariant with respect to the translation. Okay? And you can alternatively do it this. You put a probability measure here, then this transformation pushes that probability measure to near probability measure here. And you know, you look at the translations, you can easily show that this translation would yield a translation on the space of semigroups with no reference whatsoever to the Hamiltonian. You can talk about the space of all possible semigroups with certain properties, and you can talk about translation here. The same thing happens for the scaling, the rescaling of the Hamiltonian, which is this group. You can kind of push forward here, and you have a group of that is acting on semigroups. In fact, to address the question of homogenization, you can address it here. And basically, you want to know whether, so the natural question, so I'm not going, let's see if I want to erase anything. I don't have time for erasing. Maybe I do. Maybe I just write it on the palm of my hand, you know, avoiding. You see, I hate to give a talk before lunch, because if I delay, then everybody would hate me because people are hungry. So I better finish this off very quickly. Okay, so basically, the question is that now whether, so the question is whether this converges to some S bar, this semigroup converges for P almost all H. That would be a natural question to formulate here. for the homogenization. And you want to do the same thing here. You want to choose a Hamiltonian ODE and go back here. You have a probability measure here. Then you kind of figure out what does it mean to rescale things here. And so the question is basically, so you can kind of formulate it purely as a dynamical system questions. Namely, if I formulate it here, you basically have a kind of family of probability measure Pn after applying this transformation, and you want to know whether this family converges to suitable family P, that this family would be this family, the one that you started from, okay, maybe I'll put P bar. So again, you started with this guy, that would yield this guy, and via rescaling, that would you produce a family of probability measure Pn out of this P. So if this guy is translation invariant, this guy is translation invariant. But originally, this guy is not gamma invariant, and you hope that this converges, this sequence converges to some P bar, that this P bar now is going to be tau invariant and gamma invariant, and you want to kind of deduce that this P bar is concentrated on a single Hamiltonian, that Hamiltonian is H bar. That would be kind of some strategy to take. So now the question is whether this P bar is delta H bar. So this is a kind of a dynamical system formulation of this problem. So let me state some theorems. So this is kind of an old theorem that was done by myself and Tarver, and independently by Takis Tsouganidis. So in random setting, we have homogenization. If H is convex in P. And let me say another theorem, which is Ziliotto. It says that in non-convex setting, there exists a non-convex H for which there is no homogenization. Okay, which basically says that perhaps we should go for a more relaxed notion of homogenization so that you can guarantee there is a homogenization, because there would be some probability measure P bar, and that comes from taking the limit of these guys. However, you don't insist this P bar to concentrate on only one single Hamiltonian. So in the end, the randomness survives, and you have a kind of a family of candidates for H bar, and you know with what probability you observe any given H bar in the support of that measure. So that suggests the following formulation. You may kind of argue in the same way, but there are evidences that in this case, this phenomenon that was discovered by Ziliotto would not occur in symplectic setting. There are very strong evidences that even in non-convex setting, we would have a homogenization. For one thing, in collaboration with Viterbo, we can show that if for some subsequence this converges, then the full sequence converges, which is not the case if you use the viscosity solution. So if I have, do I have time? No? Okay, you know, I mean, before lunch, that's the crime to commit here. I stop.